Swayam Prabha. Digital India. Educated India.
Okay, students, so we start once again yet another lecture. This is the 8th lecture on the topic of consolidation and settlement. Let us take a look at the first slide. This shows what we have covered, particularly in the last lecture. We covered two very important concepts in the last lecture and also saw a few examples to illustrate some of the concepts we had seen a little earlier. The topics we covered were the so-called secondary consolidation and the so-called radial consolidation. Now, it is obvious that the consolidation phenomenon that we studied in the first few lectures was only due to the hydrodynamic lag, that is the expulsion of water from the pores, and because of the delay or the slow process of expulsion of water, there was a lag between the transfer of the load to the solid grains and the expulsion of the water, and so it was called a phenomenon of hydraulic or hydrodynamic lag. Now, it has been observed that even though the consolidation is say 100% complete due to this phenomenon of hydrodynamic lag, that means the entire load increment that has been applied to the soil has been transferred to the solid grains. It has been found that the settlement of the soil continues. Actually, the observation has been made in a sample in the laboratory in the odometer test. It shows that settlement continues even after transfer of the entire load increment that had been applied, and this phenomenon is due to a number of reasons, but primarily due to what is known as plastic lag, that the solid particles go on adjusting themselves even at constant stress. They continue to undergo some deformation even at constant stress and readjust themselves, and this movement, gradual movement of the particles and readjustment even under constant stress is what is known as the secondary compression behavior or secondary consolidation. In the last class, we just had a glimpse of what is secondary consolidation, a little bit about the basic reason for the secondary consolidation and its explanation. Then it was followed up with a brief mathematical explanation of three-dimensional consolidation phenomenon. You remember, we simplified the actual consolidation problem considerably. We used the concept that had been proposed or postulated by Terzaghi, and under ideal conditions we assumed that consolidation is one dimensional, that is, the load is applied vertically and the expulsion of water is also in the vertical direction, maybe in one direction or maybe in both downward and upward direction depending upon the drainage conditions. But actual phenomenon of consolidation is three dimensional, and a special case of interest of three-dimensional consolidation, which is known as the radial consolidation phenomenon, and which has got a tremendous practical application, also I exposed to you in the last class. Let us take a look at the next slide. In this lecture, we will first briefly review what we saw on secondary consolidation last time and add a little more information to it. Similarly, we will review the phenomenon of radial consolidation as we understood last time and add a little more material, and then subsequently solve a few problems. Actually, this is the penultimate lecture. There will be one more lecture, the last one, where I will be covering a sequence of examples, graded examples, give some general information and also broadly give a summary and wind up this set of lectures on consolidation and settlement. So, continuing this, let us take secondary consolidation. Let us quickly read what is here in this slide. The compression due to hydrodynamic effect is known as primary consolidation. Well, this is very well known. We have already discussed in substantial detail. The consolidation that we have been discussing all this time is primary consolidation. But some clays continue to exhibit compression and reduction of voids even beyond the primary consolidation stage at constant effective stress due to what is known as plastic lag, and this is what is known as secondary consolidation. So, this is merely an emphasis on what I had just now mentioned, that is secondary consolidation is essentially due to plastic lag. Let us take the next slide. Okay. The probable reasons or explanations or the various phenomena that are simultaneously taking place during secondary compression there are 4 in number and they are listed here in this slide. The first one is the most important point, that here the phenomenon of compression is not due to the phenomenon of expulsion of water and reduction or dissipation of excess hydrostatic pressure. So, point number 1 is this phenomenon of secondary consolidation is not governed by dissipation of excess pore pressures. Okay. Now, then what is going out? There is some water, in spite of all this water that is being expelled out of this soil going out, there is still some water. There is some water that is always adhering to the solid particles, which can only be removed by means of either some mechanical action or by means of heating. So, the well known examples are, to remove that water, we normally put the soil in the laboratory in an oven and heat it at 105 degrees for 48 hours or 24 hours as the case may be. So, this is nothing but a thermal way of removing that water which is adhering to the surface of the solid particles. A mechanical way, an example is compaction. During compaction, some amount of water also goes out, particularly that which is adhering to the solid particles do go out, but basically this water which is viscous in nature is what is driven out during constant effective stress during the secondary consolidation process. And it is during this process of viscous water moving out that plastic adjustment or deformation of the particles takes place. And so, the third point is plastic readjustment of the particles. And lastly, the particles not only just move and reorient and readjust and relocate themselves, under the effective stress sometimes they even undergo some breakage or some damage, some fracture. So, some progressive fracture, gradual fracture of some of the materials or some of the particles of the soil solids is also contributing to the secondary consolidation. So, these are the 4 phenomena that are going on simultaneously. Okay. Let us see a typical consolidation dial gauge reading versus time graph of an odometer test. Let us take a look at this slide. Here I have got the dial gauge reading and here I have got the root of time plotted. This is the well known Taylor's square root of time fitting method, the graph for this method which we had discussed earlier. My endeavor is to focus your attention on all these dial gauge readings which are shown here. D0 is the initial dial gauge reading, and when you apply a certain amount of load, it takes a little bit of time for the load to settle down and seat itself properly, and that is because some air may be there in the pores of the soil, and unless they are either compressed or expelled out, the dial gauge reading will not be stable. So, immediately on application of the load, the dial gauge reading changes to a value of ds, and in the square root of time method, this location of ds is obtained by drawing an extension of the straight line portion of this dial gauge root of time method graph. So, ds actually is a little difficult to locate, the dial gauge reading at which the actual consolidation phenomenon starts, that is the dial gauge reading ds actually corresponds to u equal to 0%. It is slightly difficult to locate this, and that is why we have this graphical procedure to locate ds in this particular method. We had also seen another graphical procedure in the log time method of Casagrande. Now, this point corresponds to 90% consolidation. If we allow further consolidation and allow the dial gauge readings to stabilize, then we come to D100, that corresponds to 100% consolidation. That means the dial gauge reading has practically stabilized. There is no noticeable change in the dial gauge reading within a reasonable period of time, or at least the change in dial gauge reading is much less than the least count of the dial gauge, and therefore cannot be detected by the dial gauge. And then if even after reaching this 100% consolidation stage, keeping the load constant, if we allow further time, after about 24 hours or a little more, the dial gauge shows a slightly different reading, and that is the real final stabilized reading, and that is the one which corresponds to the secondary consolidation stage. Next slide will show you how we compute, therefore, what is the primary part of the total consolidation that we observe in an odometer test. So, in a typical odometer test, we start with D0, go to DS, then D90, D100, and then finally DF. So, D0 to DF is the total compression, okay, and primary compression portion out of that corresponds to DS, from DS to D100, and the secondary compression part is from D100 to DF. Now, DF is usually taken after 24 hours or sometimes 48 hours. The ratio of DS minus D100, that is the primary compression part, to the total compression D0 minus DF is what is known as primary compression ratio. If we are using the logarithm of time method of determining CV, there we determine D100 directly, and therefore, that can be used in this to find out the primary compression ratio. But if we are using the square root of time method, we actually locate only 90% consolidation point precisely. 100% consolidation point is only an estimated value, it is not determined, and therefore, in order to get the primary compression ratio, we need to multiply ds minus d90, that which is what we are measuring in the experiment, by a factor of 10 by 9, so as to get or transform this into a reading corresponding to ds minus d100. Well, this is the primary compression ratio, that is the part of primary compression out of a total compression. So, the remaining part is the secondary compression. Now, a little more about this secondary consolidation. If you take a look at this curve, you find that the 60% point corresponds to something here, and the deviation from the straight line nature of the curve starts somewhere here itself. So, this makes one think as to why that deviation is occurring. It has been noticed that around 60% consolidation itself, the secondary consolidation gradually starts manifesting itself. though in a very small way, minor way, it starts coming into force even at 60% of the primary consolidation. However, we ignore this and we generally consider the secondary consolidation to be occurring only after the 90 or 100% consolidation stage of the primary consolidation. Now, where does it occur? In what kind of soils does it occur? It is particularly noticeable in micaceous clays, organic clays and other loosely deposited clays. Normal inorganic clays do not exhibit much of this secondary compression. The secondary compression is more noticeable in highly compressible material like micaceous material, organic material, etc., which are present in the clays under certain conditions of their formation. Now, how does one compute this secondary compression and how it progresses? Or in other words, in the case of primary consolidation, we were interested in two aspects, basically the total compression or total settlement and time rate of settlement or time rate of compression. In the secondary consolidation as well, it will be of interest to us to also know the rate at which the secondary consolidation proceeds, because as we saw in the discussion that just preceded, we can compute the total secondary compression from the dial gauge reading versus time curve from the odometer test data. So, the total secondary compression is easily obtainable. However, the rate at which it takes place is also important, and that can be done by approximating the EP curve again. Suppose we take the void ratio and pressure. Actually, during secondary consolidation, the pressure or the effective stress remains constant, and the void ratio therefore varies not with respect to pressure, but with respect to time for a given pressure. For a given constant load increment, the void ratio actually varies with respect to time. So, it is the E versus T curve which is of importance, and that will tell us at any given time what is the change in void ratio and correspondingly what is the amount of compression or the amount of secondary consolidation that has taken place. The change in void ratio is a direct measure of the degree of consolidation that has occurred during the secondary stage. Now, what is the relationship between E and T? As I said, this is a plastic phenomenon. The secondary consolidation is a plastic phenomenon, and basically it is logarithmic in nature, and that has been borne out by experiments with the odometer, and therefore, E versus T curve is usually logarithmic, the relationship is exponential, and therefore, we generally plot E against log T, which generally gives us a fairly linear relationship between E and T. Take a look at this slide. Here, void ratio is plotted against logarithm of time, and the relation is very nearly a straight line. I have idealized into an actual into an exact straight line here. However, in practice it will be very nearly a straight line, and it can be approximated very easily very reliably into a straight line. The slope of this straight line is obviously a measure of the relationship between E and T, and this slope, suppose that is alpha, it is this slope alpha which is a measure of the rate at which secondary compression takes place. So, let us take a look at the next slide. Suppose I take two successive void ratios corresponding to two different time periods, time instants rather, then E1 minus E2 as per this E log T curve which we saw just now during the process of secondary consolidation has to be equal to alpha times logarithm of T2 upon T1. So, the change in void ratio is alpha, the slope of the graph, into log 10 T2 upon T1. So, alpha that is coming here as the slope of the curve is the constant between the two relationships, and that constant connecting the two parameters is known as the coefficient of secondary compression. T1 and T2 are two time instants, and generally T1 is taken as the time instant corresponding to T90, and T2 is any other time during the secondary consolidation stage for which we take the change in void ratio. So, if we assume the ET relationship to be a logarithmic relationship, then we have a way to compute the rate of compression during the secondary compression stage. That is by this formula, delta E is equal to alpha log 10 T2 upon T1. So, if this straight line relationship is assumed, then the slope of the straight line can be computed by knowing two void ratios and corresponding times, and it will be simply equal to the ratio of E1 minus E2 to log T2 upon T1. So, if from an experiment we plot the ET curve and compute alpha, then that will serve us in helping to compute the degree of secondary compression at any given time. Now, we pass on to 3-dimensional compression or consolidation, particularly with reference to radial consolidation. Take a look at this slide. We have here, as I had already explained in the last lecture, an embankment sitting over a soil surface. There is a compressible soil layer here, and what you see here driven or placed or erected in this compressible soil layer are vertical drains. These are nothing but vertical boreholes which are filled with some highly pervious material like sand, and on top again there is an embankment below which at the base of which we have a horizontal drainage layer, that is a layer consisting of some highly pervious material, and this is a typical arrangement which is known as the preloading arrangement. I had mentioned in the last lecture, but let us recapitulate. Suppose we have a highly compressible soil and we want to build a structure on this, maybe a building, maybe a tank. Now, some of these buildings may not be able to withstand the time rate at which the consolidation takes place. If the consolidation takes place over a very long duration of time, these structures may not be able to adjust beyond a certain limit, and therefore, it is seen that it is advantageous in such cases to first consolidate the soil and then put the structure, because we have seen a phenomenon known as pre-compression, in which we said that in the past a soil is subjected to a certain amount of load which for various reasons is taken off later on, either naturally or artificially, by natural processes or by man-made techniques. Now, that means a certain soil, if it has already undergone consolidation under a pressure larger than what you find now, then that is a pre-compressed soil, an over-consolidated soil. And such a soil, if it is subjected to load again, until it reaches the load up to which it had been compressed in the past, it will not show any compression, or even if it shows, it will show very marginal compression only. But beyond that stress value corresponding to the previous pressure, it will start behaving like a normally consolidated soil and show compression as any other soil does. So, if we take E versus P curve, if this is the virgin consolidation curve and suppose some pressure has acted on a soil and reached a value corresponding to P maximum, and then the stress has retreated due to either natural or other causes, and once again now by building a structure we are overloading it, and up to the value of P max, pressure corresponding to P max, there will be very little compression because the soil has already experienced compression under that, and then it will continue like a normally consolidated soil beyond this point corresponding to P max. And this shows that if we apply a stress like P max on a certain soil, which in fact is going to be the stress that a building is going to apply, then what it means is that any soil which has already been pre-compressed with a pressure corresponding to that which is going to come to due to a structure will now not show any settlement, because it has already settled under the load which is expected to. So, this is taken advantage of in practice, and very often in such situations where we want accelerated consolidation, then we use a method known as the method of pre-compression or method of preloading with sand drains, preloading with sand drains. These are nothing but vertical drains filled with sand, pervious material, so that flow from the soil under pressure takes place also radially and then flows out, and the water flows out. This is to increase the number or the length of the drainage path, so that consolidation takes place faster, because we saw during primary consolidation that it is the hydrodynamic lag which is responsible for the time dependency of the compression, and obviously therefore time of compression can be considerably reduced if the rate of expulsion of water is accelerated. And this is an arrangement where an embankment is built over a natural soil, and this serves as a preload, and under this load, if with sand drains we allow this soil to get consolidated, then the soil undergoes compression due to this preload, and now after it has undergone compression, you can remove this preload and replace this with the actual structure, and since already compression has taken place, there will be no further compression and the structure can be expected to perform without distress comfortably. Now, this preloading and compression is a phenomenon of radial consolidation, because here we have water flowing radially as well, as shown by these arrows, and then subsequently water flows out vertically outward, because there is a drainage layer here which carries away the water that comes up. So, the excess hydrostatic pressure has now more avenue for dissipation, and therefore, the consolidation is faster. If you look at this, actually the compression is taking place not only radially, but also vertically. So, that is, the compression is vertical in fact, and the flow of water is not only vertical, but also radial, and therefore, we have to find out the resulting vertical compression as a result of two components. One is the usual vertical compression that takes place due to vertical flow, and another is a vertical compression corresponding to radial drainage, which is known as U radial. So, we will see the method for computing the total average consolidation U as a function of the average consolidation due to radial drainage and average consolidation due to vertical drainage. It might also be worth noting here that the preload should be applied in such a way that it does not cause failure of the soil. That is, in an attempt to accelerate the consolidation of this soil, if we indulge in some overzealous loading, that is excessive loading, then shear failure may take place. So, the over the preload that can be applied also has a limit. We need to compute the preload from point of view of ensuring no shear failure of the clay soil, and that is the preload which you can apply if that preload is equal to the load due to the actual structure. Then the actual structure when constructed will hardly experience any consolidation or any settlement, but if the preload is unavoidably less than the actual load that is going to come on the soil, then even under the actual load a little bit of consolidation will ensue. Okay. But in practice there are ways and means to apply this preload in such a way as by gradual construction, that is the embankment can be preloading embankment can be constructed in stages, so that the final required load can still be applied without causing shear failure of the soil. Now, this drainage in the radial direction is a function of the arrangement of the drains. There are two kinds of arrangements, two patterns actually, two geometrical patterns of arrangement. Take a look at this slide. There are two arrangements shown here. One is the square arrangement, another is the triangular arrangement. If you take the square arrangement, here we have dimension L, L, L here, and each dot here represents one sand drain. And what is the possible influence zone of one sand drain? It is very easy to understand that this sand drain and the adjacent sand drain here will share half the area lying between them. That is, a sand drain here, basically because it is circular in or cylindrical in shape, will have an influence zone which is also cylindrical. It will, that influence zone which is cylindrical will have a radius r, which will by a normal ordinary deduction can be shown to be equal to L by 2. So, this r is nothing but a radius which will take care of at least half the area that it can possibly cover within the square. Similarly, if you take the triangular arrangement as shown here, this circular or the cylindrical drain will cover 6 triangular areas as shown here, and each triangular area can be shown to be equal to 1/3 of the bigger triangle. Now, the sand drain must be so dispersed, so laid out that it should cover the entire area that needs to be preloaded. Therefore, as I was saying now, each drain covers half this area, but in fact, if we arrange the drains this way, then and if only half this distance is covered, then there will be several pockets within each one of these squares which will remain uncovered and therefore, this influence zone of this is so calculated that any drain here which caters to 4 of these squares will have an aerial coverage equal to 1/4, 1/4, 1/4, that is totally 1 square. Similarly, here one cylindrical drain will have 1/3, 1/3, 1/3, or in other words 6 triangles making up a certain amount of area, which will be nothing but twice the area of one triangle. Then what is the value of this capital R, which will have the same influence area as that of one square, or for that matter here what will be the influence area of a cylindrical drain which will have a radius R which will correspond to a total area coverage equal to 6 times the smaller triangles. That means, the radius of the influence zone can be computed by equating the areas. So, if I equate the area of the circle with area of a square, I can get capital R, which is the radius of the influence zone, and if I equate the area of this circle with 6 times 1/3 of the area of each triangle, then I can get the radius capital R as 0.525 L. Let us see how, the simple computation. So, when we take these two arrangements and see the computation of capital R, this is what we will find as shown in this slide. See, for square arrangement, the area of the cylindrical drain must be equal to area of one square. It is only then that the drains will be able to leave no pockets of uncovered effect. So, pi r square equal to L square will give r equal to L square by pi under root, and that is equal to 0.564 L. On the other hand, if we take the triangular arrangement, each cylindrical drain will have to cater to 1/3 of the neighboring triangle, and therefore, totally 6 triangles of this area should be equal to pi r square. So, from here we will find that 6 into 1/3 into L upon 2 into L sin 60, which is nothing but the area of a triangle. See here, L upon 2 into L, this angle is 60 degrees, because this is an equilateral triangular arrangement, and therefore, this length will be, this height will be L sin 60, and the area will therefore be L by 2 into L sin 60, which gives us finally capital R equal to 0.525 L. So, this shows that the drains have slightly smaller radius in the triangular arrangement than in the square arrangement. And if you take a look at the slide once again, the previous slide, see here, the triangular arrangement is such that the drains in one row, namely the second row here for example, are located in the middle of the corresponding drains in the upper row, and so also in the bottom row. So, the arrangement is probably a little more close and effective compared to the square arrangement. Therefore, in practice, depending upon the degree importance that is being attached to the preloading effort, if the preloading is important, very important, then we often go for this triangular arrangement, but if a square arrangement, which is a slightly more dispersed arrangement, is sufficient in any given instance, then the square arrangement will be adopted. So, the radius of that cylindrical influence zone is not just half the distance of the or half the spacing between the drains, it is more than that. Now, this shows the dimensions of the typical sand drain, that cylindrical drain which I mentioned. So, the total diameter is 2r, total influence zone has a diameter of 2r, but the drain itself has got a radius Rw, or the diameter is equal to 2Rw, where Rw stands for radius of the well. The drain is often called as the well, and this is the height